In the previous session, we looked at the conservation equations and we looked at the mass balance, which we showed was of this form. We looked at the same version of that balance in terms of concentration, and we also introduced the energy balance. And we didn't actually derive the energy balance, but we showed that by analogy, you had the same types of terms. We also showed that for the momentum balance. And of course, you've seen this in some detail in the earlier parts of the course. We also mentioned that you could get the same type of form and structure for electrostatics. So you have seen the full unpacking of the momentum balance in the earlier parts of the course. And of course, we've spent a lot of time on the mass balance. We have just mentioned the energy balance unpacking. And so what we want to do in this session is to further elaborate on that and unpack why each of the terms shown here are directly analogous to the concepts. So we have an accumulation term, and so you can see these two terms look similar, just that we have some different variables in here. We also have a convection-like term, so you can see a velocity and a nabla variable here, so velocity and nabla variable. And then you've got a diffusion-like term, so you've got a nabla squared here, and that generation term. So let's unpack why the energy balance has this specific form. So going over to our heat transfer section, we first introduced the notions of heat capacity and enthalpy. So we are probably familiar with these concepts from the earlier courses. So in physics and chemistry and thermodynamics, you've had exposure to these concepts, but for the sake of completeness, we'll just revise that here and establish our terminology. So heat capacity is, of course, the energy that's required to raise 1 kilogram of a given substance by a temperature of 1 degree. And whether it's Celsius or Kelvin, it's the same change in temperature. So once more, if you take 1 kilogram of a substance, and if you want to raise it by 1 degree, then this is the amount of energy needed to do that. So heat capacity Cpi, so we define component I to be the substance of interest. And this heat capacity is the energy required to raise 1 kilogram of that substance by 1 degree. And by the way, there's also a molar version of this. So instead of defining it on the basis of 1 kilogram, you can do it on the basis of 1 mole. And of course, you can just translate between the two heat capacities through the molar mass. So that's heat capacity. And you can also think of this as the factor by which, when you increase the temperature, you can estimate the amount of energy required, right? We'll see that just now. So that's heat capacity. And then we also define the energy content of a substance. So if we take 1 kilogram of a substance, we can also define the amount of energy that it contains. So this is a bit different to heat capacity. So heat capacity is defined specifically for raising the temperature by 1 degree. Now we are saying if we just have 1 kilogram of a substance, then we can estimate the amount of energy in that substance. And of course, that does depend on the temperature. So if you take 1 kilogram of water at 50 degrees and compare it with 1 kilogram of water at 10 degrees, there will be more energy in the 50-degree water. So anyway, we define the enthalpy Hi to be the energy content of 1 kilogram of the substance of type I. And this is temperature dependent. So we also define the change in enthalpy at a temperature T to be the absolute enthalpy at temperature T minus some reference temperature enthalpy. So we introduced the concept of a reference enthalpy because we don't like to work in terms of absolute enthalpies. You could say that the absolute zero enthalpy occurs where we have 0 degrees Kelvin. So at 0 Kelvin, you have absolute no vibrational motion, and so your substance is completely at rest. So that is the ideal reference state, 0 Kelvin. In practice, however, we can't really measure down at 0 degrees Kelvin. So the compromise we've reached over the years is that we instead choose a reference temperature that is easier to achieve. So for example, 25 degrees Celsius or even 0 degrees Celsius. So we can reach those temperatures more easily, and we can say, this is my 0 reference state. So we define the reference temperature and we define our reference state there. And then we can consider our enthalpy currently in terms of the difference between our current enthalpy and that reference enthalpy. So TR is the reference temperature and our actual temperature T that defines the enthalpy at that state. And so we can define the enthalpy difference as the increase of energy that you need to go from your reference temperature to your current temperature. And that's of 1 kilogram of the substance, as we say. So enthalpy, very dependent on temperature, and this is based on 1 kilogram of substance. And of course, you can convert that to a molar basis through the molar mass. Anyway, we'll keep talking in terms of mass, right? So that's all stated here. What's different? This is actually, so here we are just saying that at the reference temperature, you can define a reference enthalpy. And by the way, these are well tabulated. So if you look in most thermodynamics texts or in thermodynamics databases, you will be able to look up the formation enthalpy or the reference enthalpy. So this is documented and you can simply obtain this from tabulations. So we have defined then the enthalpy in terms of the reference state and the change in enthalpy. And what we can also recognize then is that there must be a relationship between the heat capacity and the enthalpy. So enthalpy tells us the energy at a particular temperature, and heat capacity is the amount of energy needed to raise the temperature by 1 degree. So if we add up all the changes over all the temperature differences, then we will get the total enthalpy change. So that's the way to view this integral, right? We are adding up the heat capacity across the different temperatures. So these are, if you like, Cp delta T's. So if we start at one temperature, we multiply by the heat capacity at that temperature times 1 degree, and then we shift it by 1 degree upwards. So if we started at 20 degrees and then we shift up to 21 degrees, then we keep adding up all the contributions from the Cp delta T's. And then that tells us the overall enthalpy change across the temperature difference from the reference state to the temperature of interest. And so that's how you can read this relationship. So this is a strict relationship that exists between the heat capacity and the enthalpy. And the heat capacity is temperature dependent. It does have often a weak temperature dependence, and well, it varies from substance to substance, how strong that temperature dependence is. If your temperature difference is small enough, and if your substance does not vary that much with heat capacity, then we can often approximate this as Cp times T minus Tr. So that's a common approximation that's used that you'll see in most heat transfer texts and so on. Now, if your temperature difference goes all the way from the freezing point, so let's say we were considering water and maybe our starting temperature was minus 20 degrees Celsius, and we were considering the difference between minus 20 degrees Celsius all the way up to 200 degrees Celsius. So if you were raising the temperature of a body of water from minus 20 degrees to plus 200 degrees, then you would imagine you would be starting out with a solid block of ice at minus 20 degrees, and you would have to heat up that water first to the melting point. So you would need that water to melt first. So you would start at your reference temperature, and then you would first integrate up to the melting temperature. So this part would tell us the energy needed just to get from minus 20 degrees to the melting temperature of water, right? 0 degrees Celsius. And then to cross over from 0 degrees into a temperature just more than that, so where you are all water, you need the latent heat of melting. So you need all that water to melt. And this is not covered by your heat capacity. Heat capacity assumes that we are in the same phase, whereas we need to reach from solid water to liquid. And so this is the energy needed to convert us from a solid block of ice into all water. Then once we are all water, we need to go from this melting temperature to the boiling temperature. So we can add up the energy requirements through the heat capacity of water in the liquid form. So this function will generally be different to the function for water in the solid phase, right? So for ice, the heat capacity is different to the heat capacity for liquid water. Then once you reach the boiling temperature, you still have to go from all liquids to all gas. So this is the latent heat of vaporization. So this is the amount of energy needed to go from all water to all gas to all steam, right? And then once you are in all steam, you are at the boiling temperature. And then our temperature of interest, the 200 degrees, is still higher than that temperature. So we are superheating the steam. So we are adding even more energy that will take that steam to an even higher energy content. So this is how you can go from how you can integrate across phase changes. And of course, we could have picked any temperature difference. You could have started instead at, let's say, 50 degrees Celsius and gone only up to 150 degrees Celsius. So in that case, if you started at 50 degrees Celsius, then this part won't apply. You don't need the melting heat. So if you've started at 50 degrees, you've already melted, you are already in the liquid form. And so you would start here. You wouldn't start at the melting temperature. You'll start at 50 degrees here. Then you have to integrate to 100 degrees. And then you do have to add the latent heat of vaporization because you were at 50 and now you are going to past 100. So you need to add that energy. And then here you integrate from the boiling temperature 100 to the desired temperature 150. So this equation you customize according to the temperature range of interest, right? So that's how you estimate the enthalpy of a component. That's how you estimate the change in energy that's needed to achieve the final temperature given a reference temperature like so. Okay, and again, that reference temperature might be below the melting temperature or it might not be. So those are the energy. That's how you keep count of the energy in the system. Right now, once we have that, I've made, by the way, we've already made these comments about weak dependence and so on. So with these basic concepts in mind, we can go ahead and apply this to the case of heat transfer. For working through this a bit better, there's this example here. So it's showing a mixture of 5 species and you are given the heat capacity and it's assumed to be constant. You're given the formation heats. This is like your reference enthalpy. So at a certain temperature, there's a reference enthalpy here. And in this question, you want to show how the net heat. Well, this is a reaction example. So through the stoichiometry, you can show how you get that heat of reaction. Okay, so that establishes one of the basic concepts. And now we want to apply this to develop our energy balances. So we want to find analogies with the accumulation term. So we are well familiar by now with determining the accumulation term in the energy balance. And we know there are other terms, right? You've got also the convection flow, and you've also got the flux, the diffusion flux. So we want the analogies to those, right? So let's start with the accumulation term. So we are familiar with, in the material balance, we can write dm dt or dc dt. And if we are really interested not in the rate of change of mass, but in the rate of change of energy, and given that enthalpy is defined on a per mass basis, so this is energy per mass of substance, then if you just multiply the mass in the space by the enthalpy, then you get the total energy in the space. So we are, of course, interested in the rate of change of energy, m dot h. And of course, we have just explained that our change in enthalpy is the actual enthalpy of interest minus the reference enthalpy. And if we recall that our reference enthalpy is a constant, right? Remember, we define the reference in terms of some fixed identified temperature. And so at that reference temperature, there is a fixed enthalpy. So that's not going to change with time. So if you go ahead and write this ddt of mh, then clearly HR dt will be a 0. So we end up with ddt of delta H and ddt of H. So ddt of H is the same as ddt of delta H, right? And so that's why we make this simplification. By the way, here, this is strictly what we have to write, but if the mass is constant, then we can remove mass as a constant of differentiation here. And so we can write it as m dh dt, and we've just said that's equal to ddt of delta H. Right. We also said that we could express the reference enthalpy in terms of heat capacity and TR. And so we can write delta H is CP minus TR. And so we can rewrite this delta ddt of delta H here as CP dt. So again, if you differentiate ddt delta H, you will get CP dt minus CP dTr dt. And so the reference temperature, that's not changing with time. So we can ignore that part. And so we are left with just this expression. And so this is looking much better now. You see, we may have had some concerns. How are we ever going to estimate enthalpy? It seems like this mysterious foreign variable. We like to work in terms of measurable things like temperatures and pressures and concentrations. So now through the heat capacity, we are able to translate an enthalpy into a temperature. And so this side of the equation is looking much better to us now, right? We've got mass, we've got temperature, time. So all those are nice, easy things. And heat capacities, we know we can look those up for given substances. Okay, so that's the accumulation term. This is the friendly version of the accumulation term for us. Okay, now let's go on to the flow terms. So looking first at our convective flux, right? First off, let's think about that in convective flux, we are typically writing U equals, the convection flux is UC. So I'm just going to make these notes here. So typically our convection flux is going to be UC. And so we expect that for the energy balance, we are going to have U times something times T. So we are looking for something of this form. And coming back here, we can say that our convective flux must clearly be, or let's not talk about flux just yet. Let's just talk about the flow rate of energy. So if we consider some control volume, then we'll have some energy flowing into the space. So again, if enthalpy is the energy content per mass, and if we have mass per time, right, the flow rate of mass, then the flow rate of mass times the enthalpy, that must be the flow rate of energy, right? So that's the flow of energy into our space. And then the flow of energy out of the space is a similar thing. We just take the mass flow rate leaving the system and multiply that by the energy content of the substance, and that will be the energy leaving the system. And if we have the mass in equal to the mass out, so if the mass profile is steady in our system, then m dot in equals m dot out equals m dot. So we can just group out the m dot, and we've got just h in minus h out here. And then we've already said our enthalpy, we can always express as Cp T minus T reference. In this case, this is enthalpy based on inlet conditions. So this must be based on the inlet temperature. And similarly, the enthalpy based on the outlet conditions, that has the outlet temperature. So, and by the way, there is a small approximation here. We are assuming heat capacity is constant over this temperature range TR to Tn. Okay, and if you look at this, you've got Cp times minus TR. So this is minus Cp TR. And then here you've got minus Cp times minus TR. So this is a plus Cp TR. So this Cp TR is canceling with this Cp TR, and left over will just be T in minus T out. So we can group all of this together like this. So we can say overall that the net change of energy due to flow is going to be the flow rate multiplied by the temperature difference multiplied by the heat capacity. Okay, and then that covers for us the change in energy due to flow rate. Then if we also look at conduction, we have that the flux of energy occurs also due to temperature differences. So if you recall in the mass case, that diffusion is based on a concentration difference driving force or chemical potential driving force. So due to the concentration difference, because any type of molecule tends to diffuse from a high concentration to a low concentration, you have a net flux from the high to the low concentration. Now we have the same concept in energy, in, I should say, thermal energy. So if there is a temperature difference between 2 points in the same material, then you will tend to have the energy moving from the high state to the low state. And this goes back to that energy always moves to the lowest energy state. It always moves to a state of equilibrium. So energy is trying to get to the space where the concentration is the same everywhere, or the temperature is the same everywhere. And that's all that this is saying. It's saying that if there is a gradient, then nature is going to move in a direction opposite to that gradient. If there's a high temperature and a low temperature, then the energy will tend to move away from the high temperature towards the low temperature. And that means the low temperature region will rise in temperature and the high temperature region will drop in temperature until the two become equal. And then this becomes zero and there's no more flux. Right, so that's the observation for energy. And so we can say that the flux of energy is equal to minus the gradient of energy. So if the temperature difference is in the x direction, then minus dt dx is proportional to the flux. And then we need some kind of constant that will help us translate the energy flux to a temperature gradient. And that is simply the conductivity, right? So any component, any substance has a certain conductivity associated with it. And so the conductivity tells us the tendency for a system to transmit energy through it, right? So conductivity, it's directly analogous to diffusivity in the energy sense. Okay, and of course the conductivity varies from substance to substance. The conductivity of copper is very different to the conductivity of, for example, paper. We know that paper has much lower conductivity than copper. So you would look up the conductivity for your material of interest, and then if you can estimate the temperature gradient, then you can estimate the flux. Right, so now we have all the concepts we need to do our energy balance. Right, once more, we needed an accumulation term, and we now have a friendly looking energy analog to accumulation. We also needed a convective flow term. This also looks friendly in quite the same way. It's written in terms of mass and heat capacity and temperature. So it has the same, it's friendlier in the same, for the same reasons that accumulation is friendly. And we have now conductivity or conduction flux. So we can see here, this is dt dx. Temperature we know is a measurable thing, and this x is our is the measurement in a spatial dimension. So this is on the order of meters. So this is measurable. We can define the space. We can define a distance down a space. So this gradient is in terms of things we can easily identify and imagine. And then conductivity, we know that the conductivity is defined quite well for many, many materials. You can go to any book with heat transfer data, and you can look up conductivities for the materials of interest. And conductivity is being measured all the time. We also have measurement devices that can be used to measure conductivity. So everything looks nice and friendly in terms of the conduction flux. Okay, so let's look at using all this now to develop an energy balance for this problem, where we have turbulent flow in a pipeline So we have a fluid flowing turbulently, if you like, in a pipeline. And this fluid has a density rho, and it's entering with a temperature T in. It says here that the mass is constant. So that means that the fluid has filled that pipeline. So the mass in the pipeline is a constant. That also tells us that m dot in equals m dot out equals m dot. And we want to develop the energy balance that we can use to get the temperature profile. Okay, so let's think about, first of all, what dimensions we need. And towards that, as you know, we always want to start with drawing a picture. So let's draw first the pipeline. And we know we've got some stream that's entering and flowing through this system. Oops. Let's draw this pipeline again. And we know we've got some stream entering here at T in. And so that's passing through the system here. And let's draw also our control volume. So we are picking an arbitrary space inside our pipeline, and we are picking it, labeling the front edge of this to be Z, and then we'll also choose here to be Z plus delta Z. So by this, I actually mean a delta, not a D like a differential or anything. So this is meant to be a delta Z. Right, so that's our, in terms of our axial direction, those are the two coordinates we need. And then we can think about the other directions. The radial direction, right, we don't expect to have any radial gradients because the problem says this is a turbulent flow. So this is a stream in turbulent flow. So because there's turbulence, then radially it will be pretty well mixed. So we don't expect temperature to vary this way. So energy is well mixed this way, but we anticipate that the temperature might be dropping down the tube. So it doesn't say it's mixed axially. So because it's turbulent, that typically means radially well mixed, but not axially. So that's pretty much what we need. And now let's look at developing each of the terms. So first off, we can talk about the geometry of our control volume. So of course, if we define R to be the radius of this pipeline, so this is R, a little arrow there, and this is R, the radius of the pipeline. Then we know that the cross-sectional area here on this edge and on this edge, the cross-sectional area there is going to be pi r squared. We can also see that the thickness of the space is going to be delta Z, right? So Z plus delta Z minus Z, that's a delta Z as our thickness of this control volume. So we can see here, the volume of our control volume is going to be pi r squared times delta Z. The area of this flat face here is going to be pi r squared. We could also define an area here. So the area on the inside curved surface of this disk, we could also estimate that. But we'll see that we don't really need that. We know that it would be 2 pi r times delta Z. Anyway, let's first estimate our accumulation term. So we said the accumulation term is ddt of the mass times the enthalpy. And now we want to estimate the amount of mass in the space. We are given the density. We are told that we have a density of rho. So we can write the mass in terms of the density by multiplying density and the volume. So we've just said that the volume is pi r squared delta Z. And so volume times density, that's the mass part taken care of. For the enthalpy, we also showed earlier that the enthalpy is Cpt minus Tr. And we know that ddt of the Tr means that Tr can go to 0. And so by the end of the day, for the accumulation term, that's what we've got left over. So just the only difference between what we saw earlier is that we have now expressed the the mass in terms of the density here. And we need to do that because we need the volume and the area and all those things together in our balance. We know that when we write our balances, we get some nice cancellations and we can develop our derivatives and so on. So we want to work in terms of the geometry. So that's why we have to work with the density here. Okay, so that's the accumulation part of our balance taken care of. And now let's talk about the mass flux. So of course, in our material balance, our mass flux, that was our convection flux, is the velocity of the fluid multiplied by the density or multiplied by the concentration. That was always our convection flux. In the case of energy, the flow of energy is going to be the mass flux times the enthalpy, right? So this is an estimate of the flux of the energy due to convection. So because the fluid is moving, because the fluid is in flow, it's carrying energy around. So that's our enthalpy flux, our energy flux, right? And of course, to convert a flux to a flow rate, we need to multiply it by the area normal to the flux. And of course, if this is due to flow, right? If our fluid is in flow, then the area normal to that flow is going to be the flat face area here, which is pi r squared. So pi r squared is that area. And so we can estimate our convection flux into the space by this. So we can say at position Z, so at this position Z, the enthalpy here we can define to be Hz. So the enthalpy is Hz. And we have to define it this way because our temperature, we suspect our temperature is changing across the space. So the temperature right here is going to be different to the temperature here. So that's why we have to be specific and call this, at this point, the enthalpy is Hz, and it's going to be different generally to the enthalpy here, which is H at Z plus delta Z, Z plus delta Z. So we've got this term for the inlet convection flux into our controlled space. And of course, for the exit from that controlled space, now it's the enthalpy at Z plus delta Z. And of course, you've got the same area. And then if we are assuming velocity is constant, then, and we know mass flow rate is the same and all that. So that's all fine. So all of this is common to both terms. So we can group that out and write it like so. And then we can expand on our enthalpy here. We can rewrite this enthalpy if we assume Cp to be approximately constant. So enthalpy at point Z is approximately Cp T at Z minus T ref. And then at Z plus delta Z, it's this. And then again, this is going to be a minus CPTR. This is going to be a plus CPTR. So those can cancel, leaving us just with TZ minus TZ plus delta Z. Okay, so that's our flow of energy due to convection. Okay, so that's the second term taken care of. And now we are also concerned about the flux due to conduction. So on top of the fluid just flowing around, you also get conduction through the fluid. And so conduction energy is being transferred due to conduction at a certain flux. So a certain flux is arriving into our controlled surface, and we have to multiply by that surface area, and it's leaving the surface, and we also multiply by that surface area. And we've already said that the flux due to conduction is conductivity times the gradient of temperature. This time the gradient is in the Z direction, so that's our flux. And then we've said the area normal to that flux is pi r squared. So that's the flux, and then we can write that in terms of the flux into the space at position Z and the flux out of the space at position Z plus delta Z. So those are our conduction fluxes. So we can stick all the pieces together. So there's our accumulation term, there's our convection term, and there are our conduction terms. And the next thing we'll do is group together the same locations. So let's just put together all the terms that are written on position Z and on position Z plus delta Z. So we actually go backwards and expand this term out into two terms in TZ and TZ plus delta Z, and then we group them with the right positions. So that's shown here. So we've split off the TZ part here, and then we've combined that with the dt dz at Z part here. And by the way, I've removed the subscript Z's because we are writing brackets around the whole thing and giving the subscript out there. So that's convection in and conduction in. And then doing the same thing was Z plus delta Z. There's convection in and conduction in. Convection out and conduction out. Okay, and if you look at this, we can do some cancellations. We've got rows everywhere. So we can, well, we don't have row here, right? So we don't have a row in the conduction terms. We do have them in the convection parts. So we can cancel that out. And we can also cancel pi r squared. So pi r squared does appear everywhere, so that can cancel. Delta Z, we don't have anywhere on the right-hand side, so we have to retain that as a 1 over delta Z. Cp, we have in the flow terms, we don't have those in the conduction terms. So when we do divide by Cp, it will vanish here and in the flow terms, but not in the conduction terms. So we have to divide by the Cp there. And that's basically it, right? We just divide by all of that and we get the equation in this form. Now, if you look at this equation, you've got a function at Z minus the same function, but at Z plus delta Z. And now we've got 1 over delta Z for all that. So it's the same form that we are familiar with, right? It has the same form of a derivative. So you've got a function at a slightly shifted value of the variable, and then you've got minus the same function at the unshifted version of the variable, and then the shift in the variable as the denominator. In this case, it's just reversed. So Z plus delta Z has a minus and Z has a plus. So we can just recognize this as minus d dz. So minus d dz of the function itself. So this is the function ut, this factor in front and dt dz, right? And we can go and do this differentiation. So in the first term, if u is not a function of z, if the velocity is not changing down the tube, we can take that out as a constant of differentiation. And we've got d dz of t, so dt dz here. And then for the second term, this is a constant in z, and then we've got just d dz of t, so that's d2t dz squared. So that's how you get that energy balance. And if you compare that with the material balance, you can see the exact same terms as we had before. We had u dc dz last time, and we had diffusivity d2c dz squared. So it's directly analogous to what we did last time, and that's why we could claim that we already had the energy balance. So this whole section, this whole lecture is just on how do we expand in terms of the same type of balance we've seen before. The boundary conditions are almost directly analogous as well. We can say that hopefully we know the initial temperature distribution across the pipe. So at T equals 0 for all Z positions, we know the temperature across that pipeline. And then we can say at the inlet point where Z equals 0, the temperature is the inlet temperature T in. And then if the pipeline is long enough, then the gradients will die out by the time we reach the end. And so we can say dt dz at Z equals the end position equals 0. So that's pretty much it. This is something we already knew, but now we've expanded on it a bit further. And hopefully we are a bit more convinced that the conservation equations do directly give us the energy balance. And like we said before, you've also got the momentum balance version of this, which you've done in detail in the first part of the course. So just go back to your conservation equations and just look at these see that this looks familiar, see that what you did in the first part of the course agrees with this kind of framework that we are putting forward here. Obviously, we've done this many times before, and now we've shown all the detail behind this, so that fully establishes for ourselves our general energy balance. That's it for today, and I'll see you in the next one.